All right, so we got about 1 minute before the lecture starts. And today is May 3rd, so I'm gonna talk about the solution of the call frame. Nope, the recursive call. Nope, no, wait. Okay, I got myself disoriented. We got this function call program that's due in 45 seconds. And we'll talk about that first. Talk about the solution. And basically, there's the sample program that I presented on the other day, which is string copy, actually shows you a good deal of the code that you need to use, because that one also uses two pointers as the. Oh yeah, it uses two pointers, just like this one, and we are copying the content pointed to by one of the parameter to the location that is pointed to by the other parameter. So for that particular part, it's almost just copy and paste. Change the name of the parameters, and that's about it. So let's see. The screen capture is on. Okay, so I am streaming on both sides, and there are people on YouTube already. So there are 12 people on YouTube. And let's see. We got about 10 more people on Discord for a total of 27 people, which means we're still missing around 20 people. At this point of the semester, that's I really cannot give people any more incentive to come to class. Um, so anyway, we're gonna get started. All right, so we're gonna get started here. By finishing the program for the swap subroutine. And then we got a very interesting program to talk about today, because it uses structures, it uses pointers, it uses members of a structure, and then it uses function calls and takes the return value of a function call as a pointer and then acts as a member that the return value of a function points to. I should say it accesses a member of the structure that is pointed to by the pointer returned by a subroutine call. Okay, so all of those things seem kind of crazy because who would stack things up like that? Well, the fact is you can. Okay, that's the whole point. Is I'm just presenting to you all the things that can be done because that would give you an idea of how things can be combined. All right, so without taking any more time, let's go ahead and take a look at the swap subroutine thing. And I think the code is in question number 4. Yep, there we go. All right. So I'll try to make this one as quickly as possible, just because we really got a lot of stuff that we need to talk about today. We only got two more lectures, to cover content of the class, and then next Tuesday is, the day when I would talk about the exam from last semester. Yes, I am refraining from calling it the practice exam, because when I call something practice exam, people start to expect, oh, so that's what my exam is going to look like. So I'm not going to make any claims now. All right, so let's go ahead and take a look at this code. This is the C code, this is the main, and you're supposed to write the swap subroutine. So what I'm going to do is I'm just going to copy and paste a bunch of stuff here. So that would be the first part. And yeah, I totally forgot that I needed to talk about this today. So otherwise I would have prepared a little bit better, but that's okay. We'll get it done. All right, so here's the C code, and then I'll also copy and paste the code from the main subroutine. So there we go. Copy and paste. There we go. All right, so now we have the necessary code. And now we can take a look. Yeah, I need to let me do this. The first 15 lines, change the beginning of each line with 2 slashes with a space. So we are commenting out just the beginning of each line. There we go. And now we can put the comments at the right place. So from line 1 to line 7, we want to move it all the way to here. So line 1 to 7, move to here. There we go. All right, so we're going to start with main first. So main has two local variables, x and y. The way I do the allocation is I allocate for variable y first, so that means y has the highest location, and then I allocate for x, and I'm going to put a no op instruction just here, so this way we can use the trace mechanism to trace the code, so that you guys can make a snapshot of that trace, so that you can also spend some time to take a look at what happens when the program executes. All right. Oh, well, that's okay. I mean, Bernard, if you did the whole thing from scratch, including main, you just got yourself a little bit more practice. That's all. So I would not look at it necessarily as time wasted, because that's actually a good thing. I mean, you just spend some time to practice, all the stuff that we have talked about. Yeah, so it's all good. It's all good. All right, so so the first thing we did was to so this is the code of main, which is not our focus today, but you might want to kind of go through all that code just to make sure that main makes sense to you. Okay, what we'll do today, what our focus is to look at swap. Just as I sent you some of the ideas to kind of understand the material. So we want to look at this from the perspective of a call frame. A call frame consists of the parameters. So PTR2 is a parameter, PTR1 is a parameter, and then we have the return address. These are all based on the agreement between the caller and the function being called. And then we have our local variable t here. So after we do all the allocation, register D should be pointing to the local variable t here, and it is important to I think it's important to associate symbolic names to the offset to each item on the stack. So some people may start to ask, why do we want to use offsets from where the stack pointer points to instead of okay, this particular label is simply the address of that thing. It's not possible because the stack changes, right? Especially when you have a subroutine that is recursive. So it's the same subroutine definition, but every single time you invoke the subroutine, the locations of everything changes. It flows with where the stack pointer is pointing to. So we can only specify the offset of those items from where the stack pointer points to, because we have no idea, by the time we get to the function, the called subroutine or the called function, where the stack pointer is actually pointing to. That depends on a lot of factors, mostly, who is calling this, right? And whoever is calling this depends on whoever is calling that, and so on. So that's why everything is relative to where the stack pointer points to. If I want to go through all the trouble, I could have done something like this. T is the first thing on the frame, so it has an offset of 0. So this is the starting point of everything. And then I have local var. Okay, I'm usually proceed with the name of the subroutine, so the LVS is not going to be there won't be any label collision. So I really should be doing the same thing with T as well. So this way we don't have any problem with using the same variable name across different functions. Alright, so this one is the size, and since t is our only variable and it has a size of 1, so this is all we need to allocate for local variables. And then we need to locate where is PTR1 relative to where the stack pointer points to. So you could just say PTR1 is 2, right? Because you can see how t is 0, return address is 1, PTR1 is 2. But I'm going to use swap LVS 1 plus. So this 1 plus has to is compensating for the byte that the return address is taking up on the in the call frame. So then PTR2 is right after that, so it's PTR1 1 plus because ptr1 itself has a size of 1. So this way I give every single item except for the return address in the call frame a symbolic name so I can refer to each one. And then swap LVS is handy because this way we can allocate and deallocate for the local variable using a fairly generic way. Now, it doesn't mean that you have to write this program in exactly this manner. Okay, some of you probably just gave constants to the labels, or you may not even be using labels at all. Which is fine. Because that's you writing the program, and when you don't use symbolic names, it really just makes the code harder to write from your perspective. Yeah, I think, oh, right, LVS, not LVR. Thank you. There we go. Thank you. Thank you, Gannon. All right, so now we're gonna do the allocation because the local variable is up to the subroutine itself or the function being called to allocate. So we're gonna have to do that first. So LDI a with swap LVS, and then we subtract that much from the stack pointer. This is how we do the allocation of the local variables. And we only have one in this case, but this code is going to work regardless of how many local variables you have. Now, when we exit, we have to be careful probably not to use register A. Now in this case we can use register A because it's a void function, but generally speaking, if you avoid using register A close to the end of the subroutine, it's usually better because just in case this is a function that returns a scalar value, you want to make sure that you don't mess up register A, because register A is supposed to store the return address. So now we also would write the usual code of getting out of the getting back to the caller. So that would be a LDAD, increment D, and JMP A in this case. It's perfectly okay to use register A for all of this stuff here because we are looking at a function that has a void return type, so it doesn't really have a specific return value. So we can use register A for whatever we want in this case. So all the code that we need to write is going to be here, and I'm just going to copy these 3 lines of code that we are supposed to write over there. Okay, so we'll paste right here, and then we'll go ahead and implement each one accordingly. I'm not going to do any shortcuts, so I'm not going to keep a particular value across statements. So it's not as optimized as it can be, because it actually can be slightly more optimized. But this way, the code is a little bit more straightforward. So we'll do a LDI A with swap PTR1. So register A now has the offset to PTR1, add AD. So now register A is the address of PTR1, which is not what we want, right? Because not only do we not want the address of PTR1, we don't want the value of PTR1 either. We eventually want what PTR1 is pointing to. So now we have LDAA, and after this we have PTR1 in register A, but that's not what we want either, so we need to dereference it one more time to get to whatever PTR1 is pointing to, which is what we want. So now we can work on the left hand side, which is T. So LDIB swap T, add BD. So register B now has the address of local variable T, and that's all we need. We need to store to whatever register B is pointing to with whatever is in register A. So that completes T equals to whatever PTR1 points to. Now we move on to the second one. As you can see, you can probably just kind of do a copy and paste and just change PTR1 to PTR2, because the right hand side has almost the same format. So for yank, and then just copy here, change PTR1 to PTR2, right? So pretty easy stuff. And then we have LDIB with swap PTR1, add BD, LDBB, and then STBA. All right, so When you get this code, I can give you guys this code, at the end of the lecture. But when you get it, it is very important that you comment this program line by line and explain what is in a register after each line of code. I spoke it out loud for some of these cases, so you probably want to re-watch the lecture, because I don't want you guys to be busy like copying stuff right now. So right now, you just need to kind of focus on what I'm talking about and get a general sense of what it is. But when you get the code, then you have all the time in the world. Well, maybe not, but you have more time to kind of think about it, create a map, go through the trace. The trace is one of the best tools to visualize, what each register is doing and what it looks, where everything is on the stack. So that is really super duper important. After line 72 is the value in register A, the constant value or the address. So line 72 is right here. It would be after, right after line 72, register A is going to have whatever PTR2 is pointing to. Just like after line 63, register A has whatever PTR1 is pointing to. All right, so line 77 is not a load because we are supposed to store to whatever PTR1 is pointing to. And after line 76, register B is PTR1. So once we dereference B one more time, we will get to the location that PTR1 is pointing to. So are we good so far with this code? Because we are close to finishing with this code already. So if anyone has any questions, now is a good time to ask. So I'll let you guys, kind of spend some time to think about, the rest of the code and post questions in the text channel. So I'm just going to go ahead and finish up this code and then we'll run it, make sure it's working, and then that'll be the end of this discussion. All right, so we want to store that to PTR2, so swap PTR2, add BD, LD, BB, and STBA. All right, so I think I'm done with this code, and secretly, I really want this program not to work because that way I can also show you how to debug a program. But I'm not sure. I did not intentionally put in any bug. Doesn't mean that I do not accidentally put in a bug. So it is entirely possible that we actually have a bug in this program. But in which case, it's actually okay. It's fine, not a problem. Because I do want to have a opportunity to show you how to debug a program. All right, so let's save the code, and then we'll go to yeah, this is the folder where I put all the exam questions for CISP440. Let's go to Documents, CISP310, and River Spider. And for those of you who cannot set up or do not want to learn how to set up a Linux-like command line environment, this is not needed. I mean, this is really not needed to get through this class. It's just a convenience feature. But to some people, learning how to set this up, in a Linux-like environment now, especially now, it's going to take up even more time than it's worth. So, so there we go. We got the code already running, and I just need to go find my assembler tab. Have no idea where I stash it. Let's see, is that it? Alrighty. I'm just looking. It went to another window, so let me drag it all the way to here. Alright, so it does look like the code that we just wrote, and I heard there's a notification in Discord. Alright, so the question is, does the ST mnemonic store the dereferenced onto the stack, or where does it store it? Alright, so how do we answer that question now? And then the second question is, so in my code, I ended up swapping the memory address in. What? No. Okay. Well, okay, so there's only one correct end result that we're looking for, which is the exchange of the content or the values of local variables x and y of main. So that's what I'll be looking for when I'm grading this. So now, having said that, it doesn't mean that my program actually get it done either. So now the question is, how do we test this program? How do we, know how do we know whether this program is working or not? Well, the first thing we need to do is to figure out, what does memory look like in this case? And that's something that I really want you guys to do to, on your own, with all the sample programs that I have written so far. Do it to every single one of those programs, because that's a very useful exercise to visualize what is on the stack. So I'm using a local spreadsheet, so this is just as a local spreadsheet using LibreOffice. And what we'll do is to look at locations, location 255, 254, 253, 252. I'm just counting the number of bytes that we actually need in this case. I think this is it. Okay, I think these are all the locations that we need. And then we have the hexadecimal representation of all of these locations, because the trace or the analysis tab displays everything in hexadecimal. So having these can be handy. Alright, so the first thing we do is we see how we use, right after the sub dd, d is going to be 0, and then after the decrement, register d is going to be 255 and then 254, and then we put the 3 to location 254, so this is going to have a content of 3, and this is actually local variable x of main. And then we increment d, we copy d to c again, and then we increment d, because we don't want to increment d unnecessarily, because remember, everything that is below where the stack pointer, which is register d, is pointing to, is susceptible to the corruption of gremlins. So we don't want to increment register d itself. So I make a copy of register d to register c, and then increment register c to change location 255 to a content of 7. So this is our local variable y of main here. That is correct. So Bernard, answered Gannon's question. All of that stuff, is in the opcode table. It is all described in the opcode table. And also in the architecture. So when you look at the TTP architecture, and you basically execute the ST instruction, you don't even have to execute the instruction itself. Okay, all you have to do is to get to the microcode pointer. All you have to do is to get to the ROM location where the instruction is implemented by controlling all the pathways between the components of the processor, and then you can actually see how the registers connect to various components. And in this specific case, you will see whatever register is specified in parentheses is the one that connects to ram.d, and whatever register that is not in parentheses is connected to register d, and then RAM is set up to be in write mode, so that one register supplies the content, and then the other register supplies the address of what changes we want to make to RAM. So that's a very simplified explanation of the ST instruction. But by now, at this point, okay, I would be expecting all of you to know that already. So if you are not familiar with those concepts and how to get that part understood, it's time to review the material and catch up. Okay, I'll just be very honest with all of you. That is expected, that you should be able to understand the ST instruction by now. Not only in the sense of what opcode table describes, but also in terms of how the pathways of the processor itself is going to be set up when we execute the ST instruction. All right. And if there are questions about when did we cover that, I have no idea. I cannot remember. Okay, it's just that we did cover that and it's recorded somewhere. So that's all I can say, because I really don't keep track. I told you guys to keep track of the date and the time of the topics. So that's why I said that at the beginning of the semester. All right, so there we go. And now we want to find out what about the rest of the rand locations. So as it turns out, I'm missing 1, 2, 3, 4. Okay, so we need 2 more locations, 251 and 250. So that would correspond to FB, and that would correspond to FA. All right, so now what we'll see is, okay, what about these other locations? Right after we initialize the local variables in main, we set up the arguments. We have to push the arguments first, and then we push the return address before we continue execution at the function that is being called. And the arguments are pushed backwards, which means the second argument is pushed first. So when we look at the pseudocode of main, the address of y is supposed to be the second argument, so it's pushed first. So that means we're going to push the address of local variable y of main, which is at location ff. So that's why location fd is supposed to have a content of 0x or hexadecimal ff. And then the next one is x, which is the first argument when we call swap. So that's going to be fe, because fe is the address of local variable x of main. Okay, so okay, thank you, Bernard, for extracting the TSV file. You guys can also just make a snapshot of the entire assembler at this point of time, because that's what we are running. I mean, I haven't shown you yet, okay? I'm just showing you in theory, just by looking at the code, statically looking at the code, I should be able to figure out this much, okay? So this one, FB, is the return address, because after we push all the arguments, we push the return address. I'm not really interested that much to know where the return address is, so I'm just going to specify return address here. And then after that is some unknown content. I don't really care what it is, but I know what it is supposed to be. I don't know what the value is, but I know what it's going to be useful for. So this is going to be local var t of swap. This is our return address. This is PTR1 from the perspective of the function. This is PTR2 from the perspective of the function. So when we want to refer to the call frame of swap, okay, that would be this chunk here. This is the call frame for swap. So that's a term that might be handy, might be useful for some of you in the future if you are going to do any type of low-level programming. And then for the rest of you, it will still be useful, because if you ever plan to write code professionally, in C or C++, at some point in time, you are going to encounter bugs that you have no idea what just happened. You call a subroutine and it returns to somewhere that nobody called in the entire program. And that's because the stack itself is corrupted. The return address itself is corrupted, and the symptom is going to be so weird. If you are just looking at it from the perspective of a high-level programming language, there will be no way to explain it. But when you start to understand what is going on the stack, okay, that the return address is on the stack and local variables are also on the stack, then you will understand how a buffer overrun, you're basically using an array out of boundary, can potentially cause weird problems to happen. Because when you just kind of change the return address to be a few bytes more, or I should say a few bytes, but just a few locations more than or less than what it's supposed to be, it will get back to the wrong place in the caller, and that can cause massive confusion. All right, so that's not the focus of today's lecture. So now, after this is all set up, this is the initial condition. Okay, this is the initial condition, and then when everything is done, the program is supposed to have exchanged the 3 and the 7. So that is what we are looking for when we run the program, after the program gets to the halt instruction, this is what we're looking for. All right, so I am going to kind of put this on the side, take a look at the analysis tab, and we want to confirm all of this stuff here. So this is what I have been suggesting in the announcements. Okay, I hope you guys read the announcements, because if I really don't have anything useful to tell you, I wouldn't be using the announcements. So in the announcements, I told you guys to kind of construct the stack by looking at the column C, because that is how we put content into memory. So we can see how FE is supposed to get the value of 0.3, and that's basically what this one is, where my cursor is located. And then FF is supposed to get 0.7. That's where this guy is going to be. FD is the second argument, which is the address of local variable y of main, and that's why it is here. And then the next one down is going to be FE. Okay, so you guys all have access to this tab, so you can actually go there independently and just kind of look through all the items. So location FC is supposed to have a content or a value of FE, and that's what this is. And then the next byte down is my return address, which is not really important to me, that I'm supposed to continue execution at location 17. And then once we get into the subroutine, location FA is supposed to be the temporary variable t. And we can see that eventually it got a value of 3, which is what we expect it to be, because it's supposed to get whatever PTR1 is pointing to, and then PTR1 itself is considered an address, which is FE, and the content at FE is indeed a 3, and that's why this is confirming that we are accessing whatever PTR1 is pointing to correctly and storing that into local variable t correctly as well. And this is basically what I would want you guys to do, when you are tracing the code. And then eventually we get to this location at this particular point here, where location FE is getting a value of 0.7, which is the first step of exchanging the two values, basically local variable x and local variable of y. So you can see how FE got a value of 0.7, matching the end result that we would like it to be. And then we have FF getting a value of 0.3, which is also matching what we expect the program to be doing. So the process of debugging is going through the effect of the program and try to match it to what you expect the program to be doing. So the moment there's a deviation where you go like, okay, wait, hold on a second here, I'm not supposed to be seeing this in the trace, then it can be one of two things, right? Because there's a deviation. Either the program is not behaving correctly, or you did not anticipate correctly. Now, sometimes you can mask a problem by having those two problems happening at the same time. So the code is wrong, but your understanding may not be entirely correct either, and they just somehow match up. So you can have one bug masking another bug, and therefore the symptoms does not show up. The likelihood of that happening is pretty slim. It does happen from time to time, but it's really kind of slim. So I hope you guys are understanding what I'm saying, when I said, use the trace not only to debug your program, but for every single program that I have written in class so far. You can go through this exercise and basically use it to reconstruct the content of the stack and understand, dynamically what are we actually doing with those instructions, because this is representing the runtime behavior of the program, as opposed to this is specifying the code itself. So they are kind of, I wouldn't say they're two sides of the same coin. They are representing different things. This is representing the instructions, and this is representing the trace, or what happens when the instructions were actually followed. And they are definitely related. Okay, one cannot replace the other one, but they are definitely related. Alright, so are there any questions about the swap subroutine before we move on to today's main item? So I'll let you guys think about it, and And since you guys all have access to this spreadsheet on your own, I am going to switch to the program that we are supposed to take a look tonight. That's not it. That's CISP310 stuff. So where's my GDB? There we go. All right. So I'm not seeing anything in the text channel. We got about 50 minutes or so, to do this. That might be a little close, but I think we can do it. Okay, so we'll see how far we can get this done. Okay. All right. So starting from this C code, line 11 to line 15 is defining a structure. The name of the struct, which is kind of the same as the name of a class, is node. And this is line 14 may look a little bit weird because can we really refer to the structure that we are actually defining right now? The answer is yes, okay, because next is not a struct node. It is a pointer to a struct node. In other words, I don't really need to know how big a struct node is in order to allocate for this specific member. Can someone tell me what is the size of a pointer in a text toy processor? In TTP, how many bytes do we need in order to specify an address? Exactly. Are you sure that's the same, regardless of whether it's an address of a location that we want to branch to versus a location of a unsigned 8-bit integer versus the location, the starting location of an entire structure? Are you guys really sure that those are all just 1 byte wide? Yep. All right. So we don't have a problem with this line then, right? Because on line 14, all we have to say is, yeah, we are still defining struct node right now, but this is just a pointer. So we'll just say, yeah, next is just taking up 1 more byte, okay, compared to V's is taking 1 more byte, taking 1 byte, and the next is going to take the next byte. That's all we need to know. And then, in other words, from the perspective of the compiler, it only needs to know that next is a pointer. It takes up 1 byte. Okay, what it points to, which is this portion here, that's for type checking. Okay, that's why C compiler, C and C++ are strongly typed languages, because when you specify a pointer, you also have to specify what kind of thing the pointer is pointing to. In assembly language programming, nobody cares. Okay, well, you care because you want the program to work correctly, but the assembler does not. The assembler does not care at all. Okay, whenever you use LD and the register is the one in parentheses, it is being used as a pointer. That's it. Okay, and doesn't do any type checking. The assembler has no concept of types. All right, so there's that, and then we have node init. Oh, okay, I forgot to specify one thing here. That is my bad. It's supposed to return p node. Otherwise, the program is not gonna. It's not supposed to work the way it's supposed to. But you guys have the link to it too. I think when I change it, you can see the changes when you click on the link. Is that correct? I just have someone to. The link to that code is at the very top of today's text channel, so you guys can kind of check to make sure that whenever I make a change here, that change is also automatically reflected when you look at it. Oh, it is? I can't hear Omir. You don't see any change. Okay, let me see if I can replicate it by using a private window. And the link is up right here. Copy the link, and paste here. Uh-oh. It did not copy the link correctly. Let me do it one more time. Copy and paste. There we go. Nope, it did not update. Huh. Okay, so I wonder what I need to do to make it update. I click save already. Probably just need to share again. Let me do another share. And that's a different link. Okay, so it does make a new link every time I update it. Okay, that was not expected. Alright, that's okay. I got it. Alright, so the text channel now has a updated link, and this one should reflect the current code. There we go. Alright, and we're gonna run the code in main. So this is the code in main. Alright, so cool. Thank you, Philip, for confirming. So this is the main code. The main code is using two local variables. Each one is a struct node. We changed the member v, of both of them. So y is going to have a value of 5, and x is going to have a value of 3 for the v member. And then we're going to go through this get this chunk of code that is kind of complicated. So I will explain it as we implement it. All right. So there we go, and we are going to copy and paste this code into, well, let's run this code first. Okay, so we're going to go through the debugger, and the breakpoint I want, we'll put one here, and then also put one here. All right, so run. Okay, we are now arriving at the first breakpoint. Print y is going to show that v has a value of 5, which is what we would expect. And then print x shows that v has a value of 3, which is also what we expect. So now when we call node init, it's going to initialize both members that p node is pointing to from the perspective of the function to 0. And it returns p node itself. So after we initialize y, the address of y returns as a, oh, this is great. So the address of y returns, as the second argument, and then after we initialize x, the address of x also returns as the return value of this particular node init. So when we call node link, it has to be done after we call node init for the address of y, and after we call node init for the address of x, and then those two return values in return become arguments to call node link. Node link is doing just this. Okay, it takes the next member of the first node and update it to be the address of the second argument, second parameter. That's basically all it's doing. So that in return is also going to return p first. So now when you look at the return value of node link, which is this entire thing, the highlighted portion of this code, that is a pointer to a structure. So with anytime you have a pointer to a structure, you can say, hey, let's look at the structure that is being pointed to by this pointer, and specifically we want to look at the member v, and in this case we want to change that to a value of 2. Okay, so that's convoluted. Okay, this is intentionally convoluted, just so that I can show you how this code is going to translate into TTP ASM. All right, so now, so after the second line, by the time we get to the return 0, that means x, the v member of x should be 2 instead of 0, because this 3 would have lost by the time we called node init. It would become 0, but when we perform this operation here, then the v member of x will actually be updated to 2. So this program, up to this point, okay, only makes use of concepts that you really should have learned in CISP310. Now, in CISP310, it's unlikely that they would expose you to this kind of code that is kind of convoluted by combining, different features of C and C++ in a weird way. Well, just because it's weird doesn't mean it's not possible. Okay, so it's really the same concepts that you have already learned. It's just being applied in a way that you normally do not see in a program. All right, so now what we'll do is we are going to copy and paste this code into an assembly file so that we can actually go work on that code. So we'll cat to, I'm just going to call this node.ttpsm. So here's the code. There we go. All right, so we're going to take out the default comment here. Take out the pound include because there are no header files in assembly language programming. And then we'll put in the comments so it's not going to complain about the C code. There we go. All right, so now all is good. All right, so the way I'm going to write this program is a little bit different from the way I wrote the other programs. I still have a no op because that's needed in order for the command line version of Logisim to work correctly. And then we're going to initialize the stack pointer just as before. Subdd is going to do the same thing, but this time I'm going to look at main as a regular subroutine. Okay, so I'm going to call main, so main is going to return just like normal, just like any other function. So now we just do a LDIA with .6 plus decrement d stda jmpi to main. So when main is all done, it's going to return to this point where we can just halt. So this chunk of code from line 1 to line 7 is actually in libc. Okay, the C library actually links in this code. So every time you wrote, every time you write a C or C++ program, there is a little chunk of code that is linked into the program that does exactly this that you normally do not see. So your main function really is just like a regular subroutine. It is called just like a regular subroutine. Now, a real main function has its own arguments, has a bunch of arguments, I should say, but we don't have to replicate that behavior here because we are not going to run this code from any command line from the perspective of the processor. So we're not too concerned about that. All right, so we're going to define the structure first, which is struct. So the compiler is responsible for inserting the code that executes main. Yes. Well, it's the okay. That's a very good question. That's a very fine line there, and I'm glad you point out the fine line. The compiler is not responsible, and rather the linker is responsible. The linker is the one responsible to bring in all the extra code that is needed to set up the environment for your program to run. The compiler is just looking at the function that you write and say, okay, I'm gonna translate your C code into quote unquote assembly code. It's called object code, but close enough. And the linker is going to look at that and go like, I'm looking for a very specific function called main, and I will insert the necessary code to set up an environment to call main, so that from your perspective, all you have to know is to say, okay, main is my entry point. So that's a good point. Thank you, Bernard. All right, so node has a member v. It is the first one, and then the next member is called next. So it is node v 1 plus, and the 1 is referring to the size of v being an unsigned 8-bit integer. Node size is going to be node next 1 plus, and this 1 is referring to the size of a pointer. It's taking up just one byte. So that's the equivalence of a structured definition, because we are just stating where we can find various members of a structure. So there we go, and I got some pollen in my eyes, and obviously that's not, usually it makes it even worse by rubbing it, but well, it doesn't seem to be any worse this time. All right, so moving right along. All right, so now we're going to write this particular subroutine. So we'll say node init. It has one single parameter. So we have node init p node, and we don't have any local variables. So in the case you don't have any local variables and you say, but I really want to just have one single way of doing things, you can always just say that local variable size is 0. So the first parameter is always going to be 1 byte after you have all the local variables. So if you want to define it this way, then this code still works. In other words, even though you have no local variables whatsoever, this is where you're going to find p node, okay, which is 1 byte above the location that your stack pointer is pointing to. And for those of you who are thinking, what about the allocation and the deallocation stuff? Well, it is not necessary because right now we can see that LVS is just a 0. But if you want to have one generic structure of code and be done with it, well, it's not gonna. This is not wrong, okay? It is not efficient from the perspective of it doesn't need to be done, but it is not wrong either. And then we also have the exit code, which is LDBD increment D and then JMPB. Alright, so now we have the template already all set up, okay? So if I decide that later on I need a bunch of local variables, I can still, the changes to this code is going to be minimal because I don't need to change line 25. Line 25 is still going to work as long as node init LVS is reflecting the number of bytes that I need for local variables. Alright, so now we're gonna implement line 19. Okay, so LDI A with 0. That's the right hand side, super easy. And then on the left hand side, it gets a little bit more interesting. So we know that we have to start with p node because that's my offset to the parameter. So it is node init underscore p node. And then an offset doesn't do me any good whatsoever, so we need to get to the address first. And then once we get to the address, we go like, okay, hold on a second here. What is in register B now? What is in register B is the address of the parameter p node. All right. And in order to do a dereference, I do not need the address of p node. I need the value of p node. So I need to do a LDB. So now register B is the parameter itself. But that's not what I'm interested in either, because what is in register B right now is the address of a struct node. Right, so it's the address of a struct node, but what we want to get to is the address of a member of the struct node. So now what we need is to use another register, let's say register C, to say, okay, what is the offset of member V of the structure that we need to access, right? So that would be node underscore V, and then we add that to register B. So after line 35, register B is going to be the address of the member V of the structure that is pointed to by p node. Okay, so I wouldn't spend too much time to write all that stuff down, but if you have any questions about what I just said, now is a good time to ask. For a program like this, when you run the program, it's always a good idea to draw the map. Okay, what is pointing where, and where is the structure, where is the member of that structure, and so on and so forth. So now that we have the address of member V of the structure that p node is pointing to, we can store the 0 into it. So stba. There we go. Alright, so that implements this line of code. Oops, that's not what I intended. Let's see, one more undo, take that out, and put that here. Alright, so the next thing we need to do is something very similar. So, as you probably would have expected, I'm just going to copy and paste and modify. Alright, so we're going to copy line 29 to line 35, copy to here. And the only thing we need to change is the name of the member. So instead of p node, instead of V, we are now changing that to next, because the structure of the code is exactly the same. except now we're trying to access a different member of the structure pointed to by p node. So this is all done. And then before we get to the end of the subroutine, don't forget that we have to specify a return value. So this line is going to be right below here. And that part really should not be difficult anymore, because we have accessed p node several times already. So at this point, it's just a matter of LDI a node init p node add ad and LD a. All right, so I'm just going to tell you, okay, when you work on commenting this code, it is very important to differentiate, the following stuff, okay? What is an offset to something in a call frame? What is the actual value of something in the call frame? And what is something that thing on the call frame, such as a parameter or local variable pointing to? So all of those things you need to really differentiate, because if you don't differentiate those things, then you can have an extra LD or have an extra ST or have missing one of them and not know about it. All right, so that's the code that I have for what is it? Init, node init. All right, so now we're going to work on the next one. And if you guys have any questions, post it into the text channel. All right, so this one is actually easier, okay? But, we are going to take a look at this one, just to find out what is on the stack. So once again, I want to look at the frame first. So I want to find out what is on the stack. Return address. And we do not have any local variables here. So once again, we can say node link underscore LVS is just 0. We do not have any local variables. And then node link, the name of the first parameter is p first, is going to be node link LVS 1 plus node link underscore p next, which is my second parameter, is where I can find the first parameter 1 plus, because the first parameter has a size of exactly 1. All right. So that should define the labels of all the items that I need to access. So the next thing we need to do is to allocate and deallocate for the quote-unquote local variables, even though we have none. So it doesn't hurt to kind of put in that code until you run out of locations. So when you run out of memory locations, then you can't really waste instructions like this. But right now we are fine. So we're gonna just kind of write this code in a very structured way. So we subtract that much from the stack pointer to allocate, and then we add that many back to deallocate, and then we have the usual return code, which is LDBD increment D JMPB. All right, so now at this point we have the entire frame set up, and we can now implement the code that we need to implement, which are these two lines. So this time I'm just going to copy and paste. So there we go. This is the first one. So this one is just a tiny little bit more complex than the ones that we have done so far, because the value that we want to use to change the member is not the constant of 0. It is whatever p next is. So we just say LDI a with node link p next, add ad, and don't forget the LDAA. So once again, I am not writing down the comment, but you should write down the comment of what is in a register, how you relate the content of a register to the C program on each line. That is important for you to do. And so when you run the code, you can actually see what is in the register, in the trace, in the analysis tab, and that way you can actually verify whether your understanding of what's in the register is correct or not. So those are the activities that you need to do in order to understand the material that we are talking about now. All right, so now we're working on the left-hand side. So the left-hand side, it cannot use register A because register A is already used. Fortunately, we have two extra registers, and that's just enough for what we need to do. So now we have node link underscore p first. Add bd st. Oops, wait, not yet. ldbb. Okay, so now we get to the value of p first, which is a pointer. We are not interested in the pointer. We're not interested in the entire structure. We're interested in just the member next of the structure that is now pointed to by register B. So now we need to use the LDI, use up the third register that is available to specify the offset to the member that we want to access. And then we add the offset of the member to the address of the entire structure, and hence now we end up with the address of the member of the structure that is pointed to by p first. So now we have the entire L value specified, and now we can do the store. There we go, store BA, and that completes that portion. And now we have to return p first. So p first is no longer here because we changed it. We still had b having the right value as a return value up to here, but because we did this extra stuff here, it's gone already at this point. So right now you kind of can think about, well, we can maybe push the value of register B here right after line 80 on the stack and then pop it later, versus recomputing it from the get-go. So as it turns out, recomputing is not any more expensive in this case. So we'll just go ahead and recompute it, from the beginning. So we have LDIA. Yeah, because we have to use register A in this case because we are trying to specify a return value. So add AD. So right now, register A is the address of the parameter, which is not something that you want to return. Okay, returning the address of a parameter or a local variable is very, very bad. Okay, that's just a super bad idea in any type of C++ program. Okay, LDAA, because we want the value of the parameter, not the address of the parameter. And that should conclude this particular subroutine. All right, so we have 20 minutes left, and I am not seeing any questions in the text channel. I hope you guys are following along, at least, in terms of the general concept. All right, so here's main. And main this time is a general subroutine, right? Because I intentionally turn main into a regular subroutine. So I'm gonna have to treat main the same way that I treat all of the other subroutines. So now we need to figure out what is on the stack. So we have local variable y, and then we have local variable x, and then we have those are the two local variables, and then before that we have no parameters except for the return address back to the caller. The caller is nameless this time. It is just the beginning of this entire code. But we have to be careful because y is not just a simple 8-bit thingy anymore, because y is now a structure. So y has two things in it. It has next as a member. It also has x has v as a member. So it takes up 2 bytes on the stack. Same thing with x. X also has its own next member and its own v member. So they take up 4 bytes altogether. So when it's time for me to define the labels, for my local variables, it will be kind of tempting just to say, okay, we have one label for v.x.v, one label for vx.next, one label for y.v, and one more label for y.next. That would have been a terrible idea because now you're locking main to the internal structure of a struct node, okay? And and the offsets to the members are now locked in. Your program becomes like really brittle. So that's not a very good idea. So instead of doing that, we're going to say x.main is going to be it's at the beginning of the entire call frame. But then when we try to define y, we are not going to define the members of x at all, because we can get to those using the node underscore labels. So we can just go define y, and even though we could have done it like this, I'm not going to do it like this. I'm going to be very structured and say we can find the local variable before, and we know the size of that local variable x. So what is the size of local variable x? And don't tell me it's 2. What would be the right thing to do here? Okay, what do we put as the question marks to basically say, okay, this is where you can find local variable y. And LVS is going to be the local variable size. This is my last local variable. This is how many bytes it's going to take. And Christopher is correct. Okay, the question mark should be node underscore size. So the use of the symbolic name allows me to change the size and the structure, and all the stuff related to node without any impact to code that is referring to node underscore size. All right, so that's how I would label everything. It has no parameters, so that's kind of nice in a way. All right, so now we need to allocate and deallocate. Remember all that good stuff. So LDI, we'll use register B, main underscore LVS, subtract that much from register D, and when we are about to return, deallocate all of that local variable stuff. So now I might as well just also define the instructions needed to return to the caller of main, which is actually anonymous. It doesn't have a name, but the structure to do that is the same. LD B D increment D JMP B. Okay, so now we try to stash all of this code here. So this really kind of belongs here. Well, I take it back. Maybe we'll put it here. There we go. And then we have the actual code, 4 lines of those, and we'll stash it here because we can only refer to x and y after we have allocated for the local variables, because otherwise we'll be using the wrong stack pointer. We'll be using the wrong address. All right. Let's see. Let me take a look at the time. It's 36. We got about 14 minutes to go. So I think we can do this, especially if I kind of shortcut a few things. I'll show you what I mean by shortcutting a few things. Okay, so so at this point we can use register A, B, and C, because return 0 is the only thing that needs to use register A. So we're just gonna say, well, that's easy. Okay, returning 0. That's done. So now we can use all 3 registers A, B, or C. Well, we'll use register A for the right hand side. Super easy. And now we need to specify, okay, where do we want to store the 5? Well, the 5 is supposed to store to member V of the structure that we call y. Now this time y is not a pointer. Y is the name of the structure. So this allows us to use a kind of a shortcut mechanism, because now I can combine the offset to y with the offset to the member of y, because both of those are just offsets, and we can combine those 2 offsets. So now we can say main underscore y being the offset to find local variable y, which is by itself a structure. It is not a pointer to a structure, and that part is really important, that it is not a pointer. It is the structure itself. And then node underscore v is the offset to find member v of a struct node. I can now just add these 2 and then add BD. So right after line 118, register B would be the address of member V of the structure that we call Y as a local variable. So this one is a shortcut, okay? But it does work, okay? So now we just have to store the right-hand side, which is already in register A, to wherever B is pointing to, because B is the address of where we want to store the 5. So that's done. Now we can just replicate these 5 lines, change a few things, and initialize, X instead. So every time I use copy and paste, that's actually very dangerous, because if I forget to update one of these things, then the program is not going to work. So I do have to be very, very careful when I copy and paste, and remind myself what I need to change between the two between the clone and the original piece of code. All right, so now we finally get to the highlight of tonight's lecture, line 126. So when you look at the code like this, what are you going to do? What would be your thoughts? Worrying is not going to help, right? So what you need to do is to think about the ordering of things. Okay, what do you need to do first? And then what do you do? 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 So I'm going to specify the ordering in a kind of using comments first. Okay, so I'm just going to label this is what we need to do first. Okay, because it is the second argument of node link, so it has to be done first. So I'm going to call this get the return value and push it on the stack first. Then we can go ahead and figure out the first argument to node link, which is this portion here. And then finally, we can call node link, which is this code here. All right, and then node link is going to return a pointer. I need that pointer in order to refer to member V of the structure that is pointed to by the return value of node link. So this is going to be 3, and once we have all that stuff, we can finally change that particular member, and that would be 4. The assignment is actually the last operation. All right, so let me pause a little bit. I know we are running a little bit short on time, but this is really kind of important. Are you guys understanding the ordering of how things happen in this case? Because that is the first thing you need to do when you see a line of code in C. You have to formulate in your mind what is the ordering of getting things done. All right, so Eric is typing. I'm going to get started here. Oh, there we go. We resolved the second parameter first because of the caller-callee agreement. Yes. So specifically, it is referring to the last argument is pushed first. That is the reason. All right. So now we're going to implement the 0, right? Step 0. So step 0 itself need us to refer to Y, get the address of Y, push it on the stack, and then call node init. Okay, so let's do that. LDIA with main underscore Y, add AD. So now register A is the address of Y. That's all we need. We now need to push it on the stack. Decrement D, STDA. So now we have pushed the address of Y on the stack. Next thing we need to push is the return address. So that's LDIA, I cannot type, LDIA dot 6 plus decrement D STDA. That's pushing the return address. Now we can continue execution at the function, which is node init. And after node init return, it'll be getting to the instruction on line 136. We need one thing we need to do is to do an increment D, because we need to deallocate the argument that is still sitting on the stack. And then we need to push the return value because the return value cannot be utilized for anything other than it is the second argument to call node link. So we need to decrement D stda because register A is the return value of the first call or step 0 of this entire thing. All right, so somebody is going to look at this code and say, but Tech, you just incremented and then decremented D. That's kind of pointless. Well, it is pointless from the perspective of they cancel out each other, but it is not pointless from the perspective of explaining that this increment D is for deallocating the argument, and then this decrement D is for pushing the return value of node init on the stack. In other words, we are setting up to call node link by using line 37 and line 38 to set up the second argument to call node link. All right. So for those of you who have watched the movie or the mini series of oh gosh, I cannot remember the name. Darn it! It was right at the tip of my tongue, and then I forgot. Good Omens, that's it. Good Omens. So the devil, one of the angels and one of the demons, basically have a contract because what they do cancels out each other's work. So they just kind of agree to do absolutely nothing. Each one would do absolutely nothing because they cancel out each other. So they decided they would just kind of enjoy life because if they both do what they're supposed to do, the world would not change a bit anyway. So anyway, that's kind of the situation that we have here on line 136 and line 137. They kind of cancel out. Anywho, we get back to our code here. So you can see how this code here is going to be, oh, Tag, you can just copy and paste again. Yeah, for the most part. Okay, so line 128 to, let's see, line 138, copy here. There we go. All right, so we got to change main y to main x because this time we're pushing the address of x to call node init. Okay, so I'm going to split the screen here. Split. There we go. So this way, the top part can refer to the C code that we are trying to implement, and then the bottom part here can focus on the actual implementation in TTP-ASM. So for the most part, yeah, we can do it like this, okay, not a problem, except for one problem. Because the stack pointer is not really the same as what it was right after we got the entire call frame set up. Because now we got that one extra thing sitting on the stack, which is the return value of the node init call with the address of y as its argument. That is now an extra item on the stack, which means when we want to get to x, we have to remember, hey, this is now 1 byte further away compared to what the label would have indicated, because the label is trying to tell us how we can find x when the stack pointer is pointing to the bottom of the call frame. But at this point, the stack pointer is pointing to 1 byte below the call frame because we have already set up one of the arguments to call node link. So that's why this is super important to kind of remember that little offset here. Okay. Other than that, things are pretty much the same. We can even keep this code here to push the return value of node init with the address of x as its argument. So after this, as you can see from the comment, we are now cool to call node link. So that means we have to push the return address, continue execution in the subroutine, blah blah blah, that stuff. So we have LDIA dot 6+. So I'm hoping you guys are now starting to see why it is a good thing that you don't have to define a label of where the subroutine is supposed to return to, because this way it is a whole lot easier to specify the code to call a subroutine. So decrement D, stda, and then we have, now that we have stored the return address on the stack, which is the last item that we need to push before we call node link, we can actually continue execution at node link now. And when it does return, we got two things that we need to clear on the stack, right? We need to increment d twice because there are two arguments. Node link has two arguments. The first one is this return value. The second one is this return value here. So those things are still sitting on the stack that I have to get rid of because they're no longer needed. So now that we have gotten rid of those two extra arguments on the stack, now we can think about, okay, so what is in register A now? What is in register A is the address of a structure, okay? Because that's what the return type of node link is indicating. And what we want to do with that return value is to say, hey, use this address to a node struct node and find its v member, and then we want to store a 2 to that place. Okay, so now we need so register A is the address of the structure, so we cannot use register A. We can use register B or C. Okay, I'm going to use register B to specify the offset to find member V of a struct node. So that would be node underscore V. That's the offset. Add AB. So now register A is the address of member V of the structure that the return value of node link is pointing to. So we now have the left hand side set up in register A. Now we need to set up the right hand side, which is super easy. I just have to remember, don't overwrite register A. But register B, hey, it's not really of any use now, so we can just overwrite that. And then we do a STAB. So we now store the value of 2 to member V of the structure that is pointed to by the return value of node link. All right, so that should be it. And oh, okay, my bad, because I forgot to put these things at the right places. So let me just kind of fix that first. There we go. Okay, so now we have the assembly code sprinkled correctly throughout the C code. And now it is time to run this program. And looking at the time, it is already 50. But I do want to go through this, okay, because it is really kind of important. Now that we have built up this program, we should know how memory should be used in this case. So I'm going to continue with this. You do have a lab tonight. You have actually 2 labs. Both are pretty easy, okay? Both labs that are due tonight, they are 3 points each, which means each one only has 3 questions. So they're not going to take up too much of your time, but both of those also has a companion portion where you have to write a program that's due in a week. So now you have overlapping because you have the overlap of oh no, you don't have overlap. Today we already have the swap subroutine turned in. So you do have 2 programs. Each lab has its own program. So both of those are due next Tuesday, because next Tuesday is our last lecture. So I do want to have everything due on that day so that I can talk about it. Perhaps in addition to the discussion of the final exam of the previous semester. All right, so having that said, now let's take a look at how the stack is going to be used. So I'm not even too interested in counting the address of the bytes at this point, because I'm just interested in what is on the stack right now. So I'm going to the first thing that's on the stack is the return address to the nameless caller, right? So it's the return address to I'll see. Let me find the right term to describe it. To halt. That's it. Okay, because when we return, it's going to get to halt. So that's the return address to halt. And then we have main. Main has 2 items. It has X and Y. So X has 2 members. Next is the second one. V is the first one. Oh, okay, never mind. Y is the one with the higher address. So y.next is here. Y.v is here. X.next is here. X.v is here. So those are the local variables that we have set up in main. So that means this part here, okay, this portion is the call frame from the perspective of main. So let me, I'm just going to give it a kind of faint background color, so this way we can see a block. So now we have to be really careful because we are going to be using and reusing bytes on the stack. So that makes it kind of tricky to demonstrate because now it's not going to be static like the other programs that we have seen before. So the next thing we do is we call, well, other than changing these things, let me go back to that code. Okay, so we do change x.v to 5, right? So x.y.v to 5, and then x.v to what? 3, I think. Yep. All right, so we do change those two locations, so that's what we can expect the program to do. But more importantly is what about that big mess of line 126, this line over here? So the first thing we did was we call node init. So in order to call node init the first time, we're going to use the stack to push the only argument in this case. So the address of y is going to be pushed first, and then the return address is going to be pushed next. And in that subroutine, it doesn't have any local variables. So when this is all done, both of these bytes will be quote unquote gone from the stack, but the return address the return value in return is going to be pushed on the stack. So we are going to have the address of y retained on the stack. It is as if we did not deallocate it because the argument turns out to be the same as the return value that we push back on the stack. But when you look at the movement of the stack pointer, it would go down all the way to the return address, and it would go back up here, and then even go back up here when we deallocate the argument. And then it will go back down here because we use code to push the return value of the first call of node init on the stack. And then after that, we call node init again, but this time we have the address of x. So we have the address of x, and then we have the return address. And then when it returns, the stack pointer will go back to this location. But then we also push the return value of node init. The first call, well, okay, this is harder to describe. The left call of node init is going to be the return value of the left call of node init is going to be pushed here, which turns out to be just the address of x itself on the stack. So this is how the stack is set up before we set up the rest to call node link. So when we call node link, this is on the stack already, which is the second argument to node link. This is the first argument to node link, and then we're going to reuse this location as the return address. And then when node link is all done, it would do several things. It would change. Oh, by the way, when we call node init, the first one is going to change both of these to zeros. So both of these locations will be changed to zeros. When we call it with the address of x, oh, I take it back. Sorry, this is the address of y. So these two locations will be changed to zeros, and then when we call it the second time, when we call node init the second time, these two locations will be changed to zeros. And then when we call node link, then we have the next of x pointing to the beginning of y. So this would now become the address of this byte here. So those are the things that would be happening on the stack if I implemented this program correctly. When node link returns, it would also return the first argument, and so the stack pointer will be this byte will be deallocated by the callee, which is node link. This byte is deallocated by these two bytes are deallocated by main. So the stack pointer would actually be back here when we are going to access the v member pointed to by the return value of node link. So it would change y.v, it would change x.v, which is this location, to a value of 2 at this, Okay, let me get back here. I know at this point you're probably kind of lost, but I still have to kind of describe it because this is getting recorded, so you can, when you watch this again, you can kind of get back to it. So when we get to 4, that's when this location here is going to change to a 2. So that's the back and forth thing that we are going to be able to see when we execute this program. If I implemented this program correctly, that is. All right. So here is the moment of truth. I know we are a little bit out of time, but this is kind of important that we get through this code today. All right. So I must have done something stupid in this process. Okay, just because it assembled doesn't mean the code is good. It doesn't mean it's logically correct. We'll see. We'll find out. So now we get back to the assembler, and we can jump all the way to the end to see. In other words, instead of reading a novel from front to back, we are now reading it from back to the first page, just so that we can see if it has a problem. Where do we find? I think it's in summary. Yep. So we have 234 lines of trace, and we can just jump all the way to the end and see if we can find the program to be doing it correctly or not. All right, so we'll see the stack pointer is balanced, and we got back to the halt instructions, so that's promising. It means I didn't mess up the stack, okay? But now we have to find out whether we stored the 2 to the location where we think it is supposed to store that, which is member v of local variable x of main. It says it's FB. Now we need to look at the spreadsheet and see if it is indeed FB. So we are looking at this location here. This is FF, FE, FD, FC, and this is indeed FB. It got the right value into location FB, but FB is changed a few times. It was changed first to 3, and then it was changed to 0, and then it was changed to 2. So now I'm just going to go through that quick look here to see if that is the case. So we're going to go start from the beginning, look at the entire column C, and then we are searching for, let's see, let's not do this, and instead we'll do a regular expression, because this way I can specify a pattern to search for. So let's see, find and replace, Control H. There we go. We want to search by regular expression, and it starts with an asterisk. It has to be escaped. FB equals 2, and that's all we are looking for. And this is at the beginning of each line, so this way, using the caret, you can specify the beginning of a cell value. All right, so let's find out. First thing is a 3, second thing is a 0, last thing is a 2. So so as far as I can do, in a quick check of whether things did happen correctly or not, everything confirmed with what I expect the program to do. All right, so that's it. Okay, so you might want to take a snapshot of the assembler right now at this point. You already have the C code because the link in the text channel is correct. The assembly code, the TTP ASM code, I can upload it right now. So give me just a few seconds here to upload that code. And then we'll talk about the lab that is released tonight. Let's see, but I'm gonna release node.ttp-asm first. There we go. All right, so the text channel now has the TTP-ASM implementation. It's really crucial that you find time to comment that program. Okay, once you get the hang of it, I know there's a lot of repetition. So if you say, okay, I think I got it, I don't have to do this like 6 times and it's the same thing. So as long as you feel comfortable about how the code works, it's okay. But I would definitely recommend commenting a portion of this program based on what you understand about what the registers are doing within this code. All right, so I'm going to shift the gear and talk about the labs tonight. There are two. They should be both, I think they are not released yet. So let me check. All right, so that's not related to what I'm about to do. Let's see, all the way down here. All right, so they are both released from the perspective of they are assigned. So now we have a recursive call and also structures and pointers. What is due tonight is in the form of a quiz. Those are multiple choice or short answers, and then the programs are due on the 10th, which is 1 week from today. Let me see if I set up any passcode for the recursive call. I think that one is fib because it's Fibonacci. Yep, it is fib. Okay, so fib is the passcode access code for the first lab. And then the second one, I'm not sure. All right, so let me check the second one. The second one does not seem to have an access code. Yeah, so the second one does not have an access code. You should be able to get in without an access code. So there you go. So you have 2 labs tonight for grand total of 6 questions. So that should not be taking too much time. Although, once it's done, I have scheduled both to release the answer so you can actually get back to the questions by the time, I'll give you guys some extra time, because I just took up some extra time here. So 10:05. So that's going to be the new due date. I'll do the same thing with the other one, but you can get started now. Here we go. All right, so I'm going to do the same thing with the other quiz, but I think you should be able to get started with the labs now. All right, so as I adjust the last bit of when it's due for tonight, if you have any immediate questions, go ahead and post your questions in the text channel. If not, I'll just go ahead and wait. All right. Yep, you guys can sign off. I'm just doing some minor adjustments of time now. All right. All right, so I'm going to get out of the channels too. I'll see you guys on Thursday. So try to get the programs done, or at least get started. So this way, on Thursday,